Lesson 8-5, Transforming Exponential Expressions. In our problems for today, we're going to be looking at comparing interest rates or just the growth rate of one item to another. To do this, we're going to have to use our formulas. The formula we're going to look at today is A times B times 1 plus the rate raised to the t power. That would be the standard form that we're going to be looking at. And we always want to make sure that our final exponent is just 1t. That means we're going to have to transform this inside a little bit. So our first question, Savewell Bank offers a savings account with 0.15% interest compounded monthly. And a second local bank offers a savings account with 2% interest compounded annually. We need to compare the monthly rates first. So to do that, Savewell is already monthly. So I'll just put Savewell here. Savewell was 0.15%. So I don't need to change that one. I just need to convert the second local bank to monthly. And they give us this as annual. Now you'll notice that they don't give us a principal amount. So the principal amount we're just going to use as 1. Then we have 1 plus the rate as a decimal. The rate as a decimal, 2% as a decimal would be 0.02. And I'm going to put parentheses in here. And on the outside, I need this to be just 1t. Okay, this is annually. That means this is written as 1, and we have to have this written as a monthly. So 1 year is the same as 12 months. So 12t would mean the same thing as 12 months. So down here, actually, this is written as 2% is written annually as 1 year. So I need to find it as monthly. That's 12t. Inside here, monthly would be 1/12. And to make this a little bit better, here I'm going to put this in parentheses here. This would be 1/12. So 1 plus 0.02, raise that to the 1/12 power. And then if I do 1/12 times 12t, I end up with 1t, which is what I want in my final answer. So when I grab my calculator, I'm going to do 1 plus 0.02. That gives me 1.02. And I raise that to the 1/12 power. That's going to give me 1.0016. And if I want to go one more decimal place, that would be 5. This all is going to be raised to the 12t power. Then to convert this to a percent, I'm just going to take what I have inside here. I have 1.00165 minus 1, and that gives me 0.00165. If I multiply by 100, that gives me a percent of 0.165%. Now there is another way you could figure this out. If we have the 2% here, and that's for one time a year, if we want to find that out monthly, you could do 0.02% and divide that by 12. 0.02 divided by 12, and then multiply that by 100. That would also give you 0.16 with the 6 repeating. So this would be roughly 0.16%. So that is another way of solving that one. Now if we're going to compare the annual rates here, so the one time a year, Savewell we need to convert. And Savewell was 0.15%. That was monthly. So if I have A equaling 1 times 1 plus the rate, this would be 0.0015. This was monthly, so I need to have it as, this is 1/12 of the year, so that means I have to raise this in parentheses here. I have to raise that to the 12th power to find out what it would be for the annual rate. So if I did 1 plus 0015 raised to the 12th power, I would have, this would be roughly 1.0181. And then if I were to subtract 1 to find the percent, I would get 0.0181 times 100 would give me roughly 1.81%. Now again, we could take the same one and take our percent of 0.15, so make that 0.0015. If I multiply that by 12, 0.0015 times 12, that would give me 0.018. And if I multiply that by 100 for the percent, I would get 1.8. So if the first method is a little more confusing to you, then use the second method and you'll still get roughly about the same amount. Second example, Lactobacillus acidophilus is a bacteria used in the production of yogurt and some cheeses. It has a growth rate of 0.92% per minute. The bacteria Bacillus megaterium is synthesized to create penicillin and has a growth rate of 0.046% per second. For this one, we need to write a function to represent the amount of Bacillus megaterium, y, that would be represent after t seconds using the effective growth rate per minute. So I'm going to have a equaling, we don't know the initial amount, so we're just going to keep it as 1. So I have 1, and then the percent would be 1.00046, and I need to raise this to the, since that's in per second, I need it to be in minutes. So this will be raised to the 60th power. All of this is in seconds, so this would be 1/60th t. Now, if I were to simplify this, I would have in here, it would be 1.028, and I'm just estimating this because if I were to put this in my calculator and did 1.00046, raise that to the 60th power, we would have 1.0279 to do it to the nearest thousandth place. Actually, to the nearest 10,000th place. So 4 decimal places. This, so tenths, hundredths, thousands, 10,000ths. This 7 tells you to move this 9 up. 9 up would be to 10. That would make this an 8. So we would have 1.0280 in our parentheses, and this is all raised to the 1/60th t. So that would be our function that we would use to represent the amount of Bacillus megaterium that would be present after t seconds using the effective growth rate per minute. Now the second part says write a function to represent the amount of Lactobacillus acidophilus y that would be present after t minutes using the effective growth rate per second. So I'm going to go back to here and I have 0.92%. So I'm going to have a equaling 1.0092 and then we are going to raise that to, since that is in per minute, so that's raised to the 1/60th. We have to put that as in per second, and then we're going to raise that to the 60th t power. Now, if I simplify that, I would take my calculator again, and we would have 1.0092. We're going to raise that to the 1/60th power. And that gives us 1.000152. So if we did to the nearest 10,000th place, we 1.000. We'll just do a little bit longer, just so longer this decimal, just so we can have a little more accurate number. We'll do 1.000153. 1.000153, and all of this is raised to the 60t power. So that would be our function for that one. And then we just compare the two, which one grows at a faster rate. Now, if I take my base and subtract 1 from both of them, so if I do the first one, your base was 1.028. If I subtract 1, I'm left with 0.028. So that one was our Bacillus megatherium. So I'm just going to label that our BM. And then our lactose acidophilus, this one, we'd had 1.000153. If we subtract 1, we would have 0.000153. And if I multiply by 100 for our percent, this would give us 2.8%. This would give us 0.0153, which would mean that this one would grow at a faster rate. Next question, Tariq is planning to invest money into a savings account. Oak Hill Financial offers 3.1% interest compounded annually. First Citibank has savings account with a quarterly compound interest rate of 0.7. What we want to do is compare. So we're going to write the function AFT that represents the balance of a savings account after T years through Oak Hill Financial if interest were compounded quarterly. So if it was compounded quarterly and they gave us the information for financial interest compounded annually. So again, we're not told what the original amount was. So we're going to use P for the principal amount, and this would be 1 plus our interest rate was 3.1% annually, so that would be 0.031. And then we're going to raise that to, so we have to find that, that was for annually. We need to find out what it would be quarterly. So this was 1T. Or actually, we could say 4 times a year, so that would be 4T. That means inside here, I have to find the 1/4 power. So on my calculator, we have 1.031. We're going to raise that to the 1/4 power. And that gives us 1.0077. We'll round that to the nearest 10,000th place. E of T equaling 1.0077. And all of this is going to be raised to the 14th power. Then it says find the effective quarterly interest rate of Oak Hills Financial around to the nearest 100th. So for this one, going back to the first one for Oak Hills, I'm going to take my base right here. And remember, in our original formula, you have A equals P times 1 plus the rate, the T power. I'm just now going to take this decimal, and we're going to subtract 1 from it, and I get 0.0077. And then I multiply by 100, and this will give us a decimal of 0.77%. So Oak Hill would have 0.77%. Part B says write a function a of t that represents the balance of savings account after t quarters through First City Bank if interest were compounded annually. Then find the effective annual interest rate of First City Bank divided to the nearest 100. So 2 decimal places. If I go back to the original problem here, First City Bank had an interest rate of 0.7. That was compounded quarterly, so that was 4 times a year. So A of t equaling 1 times 1 plus, that was 0.7, so that would be 0.007. And then I have to raise that to, so that was quarterly, that was 1/4. And I need to raise that to the 4t power. Actually, the wrong way. That was, I have to raise that to the 4th power. And this one was given us as 1/4 of the year, so 4 times a year. Now I take my answer, so I put my calculator, put this in my calculator. We have 1.007. We want to raise that to the 4th power, which will give us 1.028. And we'll go with 2 as well. Actually, we'll make that 3. Round it to the nearest 10,000th place. And this will be raised to the 1/4 t power. So now if I take this decimal, 1.0283, to subtract 1 from it, that gives me 0.0283. Multiplied by 100, we would get a percent of 2.83%. So which is the better for Greek's savings account? So we had this is First City Bank, 2.83, and if we go to the previous one, Oak Hills was 0.77. Now this 0.77, this was the quarterly, and the annual was 3.1%. And for First City Bank, this was the annual, and the quarterly was 0.7, yeah, 0.7%. So which one had a better savings account? The better one would have been Oak Hills. So that is our lesson on transforming exponential expressions.